Welcome to Whispering Atom, where the gentle mysteries of our Earth unfold like slow waves lapping against distant shores. I'm here with you tonight to explore one of nature's most patient and magnificent acts of creation, the birth of islands from the deep ocean floor through the quiet power of volcanic forces. As you settle in wherever you are, let me know where in the world and at what time you're listening. Are you nestled comfortably in your bed, perhaps near a window where you can imagine the vast ocean stretching toward the horizon? Or maybe you're resting in a favorite chair, wrapped in soft blankets as the day's activities finally fade away? Tonight, we're going to witness something truly extraordinary, the slow, gentle birth of land from the sea itself. We'll follow the patient journey of molten rock as it rises from the deepest parts of our planet, travels through miles of ocean water, and eventually creates entirely new pieces of land where none existed before. These aren't violent explosions or destructive forces, but rather one of the most beautiful examples of how our Earth creates and nurtures new environments for life to flourish. Don't worry about understanding every geological detail as we journey together tonight. Let the concepts flow over you like warm water, carrying away any tension from your day. Some ideas will settle into your mind immediately, while others will drift and swirl until they find their perfect place in your understanding. The goal isn't to memorize or analyze, but simply to marvel at the incredible patience and artistry of our living planet. Now, get comfortable. Adjust your pillow, pull that blanket up to just the right height, and let your breathing slow to match the unhurried rhythm of geological time. Take a slow, deep breath in, and as you exhale, feel yourself sinking deeper into this moment of peaceful exploration. We're about to embark on a journey that spans millions of years, but moves with the gentle persistence of flowing honey. Imagine, if you will, that you could witness the birth of the Hawaiian Islands, or the formation of Iceland, or the emergence of any of the volcanic islands that dot our planet's oceans. These islands didn't appear suddenly or dramatically. They grew slowly, patiently, grain by grain and layer by layer, in a process so gentle that if you could watch it happening, it would be like observing the world's slowest garden growing from the depths of the sea. The story we're about to explore is happening right now, beneath the waves of our oceans, in places where new land is quietly being born. It's a story of heat and pressure, of rock and water, of the incredible forces that shape our planet working together in perfect harmony to create something beautiful and new. Are you ready to descend into the peaceful depths and witness the gentle birth of islands? Then let's begin this soothing journey into one of Earth's most magnificent creative processes. Far beneath your feet, deeper than the deepest ocean trenches, deeper than any human has ever traveled, something magnificent is stirring in the darkness. Picture, if you will, a realm that exists nearly 2,000 miles below the Earth's surface, in a place called the mantle, a vast region of rock that, despite being solid, flows like the thickest honey when viewed across the spans of geological time. In this deep, hidden world, the temperature reaches nearly 3,000 degrees Fahrenheit, yet the immense pressure prevents the rock from melting completely. Instead, it exists in a state that's difficult to imagine from our surface perspective, solid enough to transmit earthquake waves, yet fluid enough to flow in great, slow currents that take millions of years to complete a single circulation. These deep currents in the mantle are like the world's most patient rivers, flowing in vast, circular patterns called convection cells. Imagine heating a pot of thick soup on your stove. The hot soup at the bottom rises to the surface, cools, and then sinks back down, creating a gentle circulation pattern. The Earth's mantle works in much the same way, but instead of taking minutes, these cycles take tens of millions of years to complete. Within this slow-motion dance of flowing rock, something special occasionally happens. In certain places, deep within the mantle, the rock becomes slightly hotter than its surroundings. This temperature difference might be only a few hundred degrees, but in the context of the deep Earth, this is enough to create what geologists call a mantle plume, a column of slightly hotter, slightly more buoyant rock that begins its incredibly slow journey toward the surface. Picture this mantle plume as an invisible river of warm rock, rising like a column of warm air on a summer day, but moving so slowly that it would take millions of years to travel from its birthplace deep in the mantle to the ocean floor above. The plume is enormous, hundreds of miles across at its base, yet rises with the patience of growing mountains, pushed upward by the subtle differences in density between the hot rock of the plume and the cooler rock that surrounds it. As this vast column of heated rock begins its journey upward, it carries with it the potential for something extraordinary. The rock within the plume contains all the chemical ingredients needed to create new land, silicon and oxygen that will form the backbone of volcanic rock, iron and magnesium that will give strength to future mountains, and dozens of other elements that will eventually nourish the first plants to grow on the new land that this plume will create. The journey of this rising rock is one of the most patient processes in nature. Moving at speeds measured in inches per year, the mantle plume rises through the deep earth like a slow-motion fountain of molten potential. For millions of years, it encounters nothing but more solid rock, gradually heating and softening the material it passes through, creating a column of slightly more fluid rock that extends from the deep mantle toward the surface. As the plume rises, the pressure around it gradually decreases. This reduction in pressure has a remarkable effect on the hot rock within the plume. Just as water boils at a lower temperature at high altitude where air pressure is reduced, the rock in the mantle plume begins to melt as it rises into regions of lower pressure. This process, called decompression melting, is one of the most important mechanisms by which our Earth creates molten rock, or magma. The melting doesn't happen all at once, like an ice cube dropped into hot water. Instead, it's a gradual process that occurs over hundreds of thousands of years as the plume continues its patient ascent. The first materials to melt are those with the lowest melting points, certain minerals rich in silicon and aluminum that will eventually form the lighter-colored rocks of volcanic islands. These early melts are like the first drops of water from a slowly thawing glacier, the beginning of a process that will eventually create vast quantities of liquid rock. As more and more of the rising plume begins to melt, something beautiful happens. The liquid rock, being less dense than the solid rock around it, begins to separate from its solid matrix, like oil separating from water. These early droplets of magma are incredibly hot, nearly 2,000 degrees Fahrenheit, and they begin to collect in small pockets within the rising plume, gradually growing larger as more material melts. The magma that forms in these deep regions has a composition that reflects the ancient history of our planet. It contains elements that were incorporated into the Earth during its formation 4.6 billion years ago, mixed with materials that have been recycled through the planet's interior countless times. This magma carries within it the chemical signature of deep time, a liquid record of processes that have been operating since our planet was young. As the mantle plume continues its rise and more material melts, the individual pockets of magma begin to connect with each other, forming larger and larger accumulations of liquid rock. These magma bodies grow slowly, fed by the continuing melting of the rising plume, gradually increasing in size and beginning to develop their own buoyancy that will eventually drive them toward the surface. The temperature and composition of this deep magma determine many of the characteristics that the future volcanic island will possess. Magma that is rich in iron and magnesium will create dark, dense rocks when it eventually cools and solidifies. Magma that contains more silicon and aluminum will create lighter-colored, less dense rocks. The deep stirring we're witnessing now is setting the stage for the type of landscape that will emerge millions of years in the future. But the creation of magma is only the beginning of the story. This liquid rock, born in the deep stirring of the mantle, must now begin its own journey toward the surface, a journey that will take it through miles of solid rock, across the ocean floor, and eventually into the sunlight where it will begin to build the foundation of a new island. The pressure at these depths is enormous, thousands of times greater than the atmospheric pressure at the Earth's surface. This pressure keeps the magma under tight control, preventing it from expanding or moving quickly. The magma accumulates slowly, building up pressure gradients that will eventually drive it upward, but always constrained by the immense weight of rock above. As you rest there now, breathing slowly and peacefully, you might imagine this deep stirring happening far beneath the ocean floor. Somewhere under the Pacific Ocean, under the Atlantic, under every major ocean basin, these ancient processes are quietly at work, creating the potential for new land to emerge from the sea. The rock that will eventually form future islands is melting right now, deep in the Earth's mantle, beginning its patient journey toward the light. The timescales involved in this process are almost beyond human comprehension. The mantle plume that creates a volcanic island might begin its journey in the deep Earth tens of millions of years before the first volcanic rock appears on the ocean floor. The deep stirring we're imagining tonight has been going on since before there were complex life forms on Earth, and it will continue long after our current continents have been reshaped by geological forces. This perspective can bring a profound sense of peace and patience. The Earth works on timescales that dwarf human concerns, creating beauty and new life through processes that are measured not in years or decades, but in millions and tens of millions of years. The volcanic islands that we see today, Hawaii, Iceland, the Galapagos, the Azores, all began with the same deep stirring that we've been following tonight. The mantle plume that created the Hawaiian Islands began its journey in the deep earth when the dinosaurs still ruled the land. The deep stirring that will eventually create new islands millions of years in the future is beginning right now, far beneath the ocean floor, in places where no human will ever travel, but where the Earth's creative forces are quietly at work. As the magma continues to accumulate in the deep earth, it creates what geologists call a magma chamber, a large accumulation of liquid rock that serves as a reservoir for the volcanic activity that will eventually reach the surface. These deep magma chambers are like underground lakes of liquid rock, fed by the continuing melting of the mantle plume above and gradually growing in size and complexity. The magma chamber doesn't form all at once, like digging a hole and filling it with liquid. Instead, it develops gradually over hundreds of thousands of years as the rising plume continues to melt and contribute new magma to the growing reservoir. The chamber grows by intrusion, new magma forcing its way into cracks and weaknesses in the surrounding rock, gradually displacing solid rock with liquid magma. As the magma chamber grows, it begins to affect the rock around it. The intense heat of the magma, nearly 2,000 degrees Fahrenheit, slowly warms the surrounding rock, causing it to expand and creating the first subtle stresses that will eventually lead to fractures in the rock above. This thermal expansion is incredibly gradual, occurring over thousands of years, but it's the beginning of the process that will eventually allow magma to find its way to the surface. The chemical composition of the magma continues to evolve as it sits in the deep chamber. Different minerals crystallize out of the liquid at different temperatures, changing the composition of the remaining liquid. Lighter elements tend to concentrate in the upper parts of the chamber, while heavier elements settle toward the bottom. This differentiation process creates magmas with different properties that will eventually produce different types of volcanic rocks. The growing magma chamber also begins to generate its own pressure. As more and more liquid rock accumulates, the chamber seeks ways to relieve the building pressure. The weight of the rock above creates enormous downward pressure, but the buoyancy of the hot magma creates upward pressure. The balance between these forces determines when and how the magma will eventually begin its journey toward the surface. The deep stirring that we've been following represents one of the most fundamental processes in Earth's evolution, the way our planet creates new material and brings it to the surface. This process has been operating for billions of years, creating the continents we live on and the ocean floor we've never seen. It's a reminder that our Earth is not a static, unchanging ball of rock, but a dynamic, living world that is constantly creating and recreating itself. As you continue to rest there, feeling the gentle rhythm of your breathing, You might imagine the deep magma chamber slowly growing beneath some distant ocean floor. The liquid rock that will eventually build a new island is accumulating right now, heated by the Earth's internal fires, waiting patiently for the moment when pressure and opportunity will allow it to begin its journey to the surface. The deep stirring continues, as it has for billions of years, and as it will for billions more. In the darkness far below, liquid rock flows and accumulates, carrying within it the potential for new land, new landscapes, and new homes for life. The patient Earth works its slow magic, creating beauty from heat and pressure, turning the simple elements of rock and fire into the complex, wonderful islands that will one day rise from the sea to greet the sun. Now, as you rest there with an understanding of the deep stirring that begins our story, let me take you on a journey through the patient accumulation of pressure that builds in the hidden chambers far beneath the ocean floor. This is where the gentle forces we've been following begin to gather strength, not through violence or sudden action, but through the slow, inexorable process of liquid rock seeking its way toward the light. Picture, if you will, the magma chamber that has been growing deep beneath the ocean floor over hundreds of thousands of years. This vast reservoir of liquid rock, perhaps 50 miles below the seafloor, has gradually expanded from small pockets of melted material into a complex system of interconnected chambers and passages. The magma within these chambers glows with an inner fire, heated to temperatures that would vaporize any surface material instantly, yet contained by the enormous pressure of miles of solid rock above. The magma chamber itself is not a simple cavity carved out of solid rock, like a cave filled with liquid fire. Instead, it's a complex, three-dimensional network of interconnected spaces where liquid rock has gradually displaced solid rock through a process so slow and gentle that it can barely be detected even with our most sensitive instruments. The chamber has grown by intrusion, with new magma slowly forcing its way into cracks and weaknesses in the surrounding rock, widening these openings over thousands of years until they become substantial reservoirs of liquid rock. Within this hidden chamber, the magma is in constant, slow motion. Convection currents, driven by temperature differences within the liquid rock, create gentle circulation patterns that mix and homogenize the magma over thousands of years. Hotter magma, near the bottom of the chamber, slowly rises toward the top, while cooler magma, near the roof, slowly sinks downward, creating a circulation that ensures the chemical composition of the magma remains relatively uniform throughout the chamber. As this circulation continues over geological time, something beautiful and complex begins to happen. Different minerals within the magma crystallize out of the liquid at different temperatures, and these crystals, being either denser or lighter than the liquid magma, begin to separate according to their weight. Heavier crystals, rich in iron and magnesium, slowly settle toward the bottom of the chamber like an incredibly slow-motion snowfall. Lighter crystals, rich in silicon and aluminum, tend to float upward toward the roof of the chamber. This process, called fractional crystallization, gradually changes the composition of the liquid magma itself. As heavy minerals crystallize and settle out, the remaining liquid becomes progressively richer in lighter elements. As light minerals crystallize and float upward, different layers of magma with subtly different compositions develop within the chamber. These compositional changes will eventually influence the type of volcanic rock that forms when the magma finally reaches the surface. The pressure within the magma chamber is extraordinary, created by the immense weight of miles of solid rock pressing down from above. This pressure is measured in thousands of times the atmospheric pressure at Earth's surface, enough to compress any gas into liquid, enough to prevent the magma from expanding despite its enormous temperature. The pressure acts like a lid on a pressure cooker, keeping the magma contained and preventing it from moving upward too quickly. But as the magma chamber continues to grow, fed by the ongoing melting of the mantle plume below, this pressure begins to build in a different way. Each new injection of magma from the depths adds to the total volume of liquid rock in the chamber, and this additional volume creates stress in the surrounding rock. The chamber walls, heated by the magma to temperatures far above their normal range, begin to weaken and expand, creating the first subtle changes in the structure of the rock above. The expansion of the magma chamber is not a sudden or violent process. Instead, it occurs over thousands of years, with the chamber growing by perhaps a few feet per century as new magma is added and existing magma continues to heat and soften the surrounding rock. This slow expansion creates what geologists call a pressure gradient, a gradual increase in stress that spreads outward from the chamber like ripples in a very, very slow pond. As the pressure builds, the rock above the magma chamber begins to respond in ways that are almost imperceptible on human timescales, but dramatic when viewed across geological time. The solid rock, heated from below and stressed by the expanding chamber, begins to develop tiny fractures, hairline cracks that are initially too small to see, but that represent the beginning of the pathways that magma will eventually follow to reach the surface. These initial fractures form along the weakest planes in the rock, following existing joints, bedding planes, and other structural features that represent zones of relative weakness. The fractures don't appear suddenly, like cracks in breaking glass. Instead, they develop slowly over thousands of years as the stress from the expanding magma chamber gradually overcomes the strength of the rock. The formation of these fractures is influenced by many factors: the type of rock above the magma chamber, the depth of the chamber, the rate at which new magma is being added, and the local geological structure of the seafloor. In some cases, the fractures form in roughly circular patterns around the chamber. In others, they follow linear zones of weakness that might extend for many miles across the ocean floor. As the fractures develop, they create new opportunities for the pressurized magma below to find release. The magma, under enormous pressure and seeking any available pathway upward, begins to probe these new fractures like water finding its way through cracks in a dam. Initially, the fractures are too small and too constrained by pressure to allow significant movement of magma, but they represent the beginning of the conduit system that will eventually carry magma to the surface. The process by which magma begins to move into these fractures is called magma intrusion, and it's one of the most patient processes in geology. The magma doesn't rush into the fractures like water through a broken pipe. Instead, it seeps into them slowly, gradually widening the cracks through a combination of pressure and chemical action. The hot magma reacts with the rock walls of the fractures, altering their chemical composition and making them more susceptible to further widening. As magma moves into the fractures, it begins to create what geologists call dikes, sheet-like intrusions of magma that cut through the existing rock structure. These dikes start as incredibly thin intrusions, perhaps only inches wide, but they gradually grow wider over thousands of years as more magma is forced into them. The dikes serve as conduits, connecting the deep magma chamber with the rock layers above and creating the plumbing system that will eventually carry magma to the surface. The formation of dikes is a self-reinforcing process. As magma moves into a fracture and begins to widen it, the reduced pressure in that fracture draws more magma from the chamber below. The additional magma widens the fracture further, which allows even more magma to enter. Over geological time, what began as a hairline crack can grow into a substantial conduit capable of carrying large volumes of magma toward the surface. The dikes don't necessarily form in straight lines from the magma chamber to the surface. Instead, they follow the path of least resistance through the rock, which may involve complex three-dimensional routes that wind around stronger rock formations and follow zones of weakness. Some dikes branch and merge with others, creating complex networks of magma-filled fractures that extend outward from the central chamber like the branches of an underground tree. As the dike system develops, it begins to relieve some of the pressure in the main magma chamber. Magma that moves into the dikes reduces the total volume of liquid rock in the chamber, which temporarily reduces the pressure on the chamber walls. However, this relief is only temporary, as the continuing melting of the mantle plume below continues to add new magma to the system, eventually building pressure once again. The temperature of the magma as it moves through the dikes is still enormous, typically around 1,800 to 2,000 degrees Fahrenheit. This intense heat has a profound effect on the rock through which the magma passes. The rock immediately adjacent to the dikes is heated to temperatures far above anything it has experienced since its formation, causing it to expand, alter its chemical composition, and become more susceptible to fracturing. This thermal alteration creates what geologists call a metamorphic aureole around each dike, a zone of rock that has been changed by heat and chemical interaction with the magma. The width of this altered zone depends on the size of the dike and the duration of magma flow, but it can extend several feet or even several yards into the surrounding rock. The altered rock often becomes harder and more resistant to erosion than the original rock, which can influence the eventual landscape of the volcanic island. As the dike system becomes more extensive and more magma moves through it, the pressure dynamics of the entire system begin to change. The magma chamber, originally a single large reservoir, begins to evolve into a more complex system with multiple smaller chambers connected by the growing network of dikes. This evolution creates a more distributed system that can respond more flexibly to changes in pressure and magma supply. The chemical composition of the magma also continues to evolve as it moves through the dike system. Interaction with the surrounding rock can add new elements to the magma or remove others, changing its chemical signature and influencing the type of volcanic rock that will eventually form. The magma may also cool slightly as it moves away from the main chamber, causing different minerals to crystallize and further altering its composition. The pressure building in this deep system is not uniform throughout. Different parts of the dike network may experience different pressures depending on their connection to the main chamber, their depth, and the local rock structure. This pressure variation creates a complex dynamic where magma may move preferentially through some parts of the system while other parts remain relatively inactive. As you rest there now, breathing slowly and peacefully, you might imagine this complex system of pressure and heat developing far beneath some distant ocean floor. The magma chamber, glowing with internal fire, slowly expanding and feeding magma into the growing network of dikes that probe upward through miles of solid rock. The pressure building gradually, inexorably, creating the forces that will eventually drive magma to the surface and begin the birth of a new island. The timescales involved in this pressure-building process are vast, often spanning hundreds of thousands or even millions of years. The dike system that will eventually feed a volcanic eruption might take longer to develop than humans have existed as a species. Yet the process continues with patient persistence, driven by the fundamental forces that power our planet's geological activity. The beauty of this process lies in its gradual, systematic nature. There are no sudden explosions or violent ruptures in this deep realm. Instead, there is only the slow, steady application of heat and pressure, the patient widening of fractures, the gradual building of the plumbing system that will eventually carry liquid rock from the deep earth to the surface. It's a process that exemplifies the way our planet works, through small, incremental changes that accumulate over vast periods of time to create profound transformations. The pressure building in the darkness beneath the ocean floor is like the slow filling of a vast reservoir. Each day, each year, each millennium adds a little more stress to the system, widens the fractures a little more, extends the dike network a little further toward the surface. The system approaches a threshold, not suddenly or violently, but with the same patient persistence that characterizes all of the Earth's creative processes. As the pressure continues to build, the stage is being set for the next phase of our story. The moment when this deep system finally finds a pathway to release its accumulated energy and begins to deliver magma to the ocean floor above. But that moment, when it comes, will not be a sudden explosion or catastrophic release. Instead, it will be the natural culmination of millions of years of patient preparation, as gentle and inevitable as the rising of the sun. The magma chamber and dike system that we've been following represent one of the most remarkable examples of how our Earth builds pressure and energy over geological timescales. This pressure, accumulated over eons, will eventually power the creation of new land, new landscapes, and new opportunities for life. The darkness far below is not empty or inactive. It's filled with the potential for creation, with liquid rock that carries within it the power to build islands and continents. As you continue to drift toward deeper relaxation, you might find comfort in knowing that these vast processes are always at work beneath our feet, building the pressure that will eventually create new beauty in our world. The Earth's creative forces work with infinite patience, never rushing, never forcing, but always moving toward the moment when pressure and opportunity combine to bring new land into being. The darkness beneath the ocean floor is not truly dark. It glows with the heat of liquid rock, with the slow fire of geological creation. In that warm, pressurized realm, the foundations of future islands are being laid, one crystal at a time, one fracture at a time, one increment of pressure at a time. The pressure builds in the darkness, patient and persistent, preparing for the gentle moment when liquid rock will finally begin its journey to the light. Now, as you rest there with an understanding of how pressure builds in the deep chambers beneath the ocean floor, let me take you to witness one of the most significant moments in the birth of an island, the first gentle crack that allows magma to begin its journey toward the surface. This is not a violent rupture or explosive breakthrough, but rather a quiet yielding, like the first tiny opening of a flower bud that has been waiting through a long winter for the perfect moment to bloom. Picture, if you will, the seafloor in the middle of a vast ocean, perhaps 2 or 3 miles beneath the surface waves. Here, in the eternal darkness where no sunlight has ever penetrated, the ocean floor stretches in gentle undulations across the abyssal plain. The sediments that cover this ancient seafloor have been accumulating for millions of years. Fine particles of clay and organic matter that have drifted down like snow through the water column, creating a soft blanket that muffles all sound and movement. Beneath this quiet sediment layer lies the oceanic crust, formed millions of years ago when molten rock erupted from mid-ocean ridges and slowly cooled as it moved away from its birthplace. This oceanic crust, composed primarily of basalt, a dark, dense volcanic rock, has been the stable foundation of this part of the ocean floor for tens of millions of years. It has weathered countless storms above, felt the gentle rain of sediments, and hosted communities of deep-sea life that have come and gone across geological ages. But now, far below this ancient seafloor, the pressure that has been building for hundreds of thousands of years in the deep magma chambers has reached a critical threshold. The network of dikes that we followed in our previous journey has extended upward through miles of solid rock, growing wider and more complex with each passing millennium. The liquid rock within these conduits has been probing patiently for zones of weakness, following fractures and joints in the rock like water, finding its way through the smallest cracks. The moment of breakthrough doesn't announce itself with fanfare or violence. Instead, it begins with the subtlest of changes, a microscopic widening of fracture that has been slowly developing for thousands of years. Deep beneath the seafloor, perhaps 10 miles down, a particularly persistent finger of magma finally encounters a zone of rock that has been weakened by millions of years of thermal cycling, chemical alteration, and the slow accumulation of stress. The rock in this critical zone has been heated and cooled countless times by the proximity of the magma chamber below. Each heating cycle caused the rock to expand slightly, while each cooling cycle caused it to contract. Over geological time, this thermal cycling created microscopic fractures throughout the rock, weakening its overall structure and creating zones of particular vulnerability. It's one of these thermally weakened zones that provides the magma with its first real opportunity to move significantly upward. The initial breakthrough is incredibly gentle. The magma, under enormous pressure from the weight of rock above and the continued injection of new liquid rock from the chamber below, begins to seep into the weakened zone like water, slowly soaking into dry earth. The temperature of this ascending magma is still extraordinary, around 1,800 degrees Fahrenheit, hot enough to soften and partially melt the rock it encounters, gradually widening the pathway for its upward movement. As the magma moves into this new zone, it creates what geologists call a sill, a horizontal or gently inclined sheet of magma that intrudes between existing rock layers. Unlike the nearly vertical dikes that connected the main chamber to this level, the sill spreads laterally, following planes of weakness in the rock and gradually growing in extent as more magma is fed into it from the dikes below. The formation of this first major sill represents a crucial step in the island building process. The sill acts like a staging area, a temporary reservoir where magma can accumulate before continuing its journey upward. As magma fills the sill, it begins to exert pressure on the rock layers above, gradually weakening them and preparing them for the next phase of upward movement. The sill doesn't form all at once, like inflating a balloon. Instead, it grows incrementally over thousands of years as successive pulses of magma are injected into it from the feeder dikes below. Each new injection of magma slightly increases the pressure in the sill and extends its boundaries a little further. The process is so gradual that the overlying rock has time to adjust to the new stresses, preventing sudden or violent failure. As the sill continues to grow and accumulate magma, it begins to affect the physical properties of the surrounding rock. The intense heat of the magma causes the overlying rock to expand and become more ductile. Chemical reactions between the magma and the surrounding rock alter the mineral composition of both materials, creating new types of rock with different physical properties. These changes gradually weaken the rock above the sill, preparing it for the next stage of magma ascent. The pressure from the growing sill begins to create new fractures in the rock above, but these fractures form in a very different pattern from those that developed around the deep magma chamber. Because the sill spreads the pressure over a much wider area, the fractures that form above it tend to be more evenly distributed and less concentrated. These fractures become the pathways for the next generation of dikes that will carry magma from the sill toward higher levels in the crust. The chemical composition of the magma in the sill begins to evolve as it interacts with the surrounding rock and as it slowly cools in its new environment. The magma may assimilate some of the crustal rock it encounters, incorporating new chemical elements that change its overall composition. It may also lose some of its dissolved gases as the pressure decreases slightly in the sill environment. These chemical changes will influence the behavior of the magma when it eventually reaches the surface. As more magma accumulates in the sill, the system begins to develop what geologists call a magma focusing effect. The sill acts like a funnel, collecting magma from the distributed dike network below and concentrating it into a smaller number of pathways that probe upward toward the surface. This focusing effect is crucial for the development of volcanic activity, as it creates the conditions necessary for sustained magma flow to the surface. The temperature of the magma in the sill remains extremely high, despite the cooling effect of the surrounding rock. The large volume of magma in the sill acts as a thermal reservoir, maintaining high temperatures through the latent heat released as some of the magma slowly crystallizes. This thermal reservoir effect helps to keep the pathways above the sill warm and ductile, facilitating the continued upward movement of magma. The formation of the sill also marks the beginning of more dramatic changes in the structure of the seafloor above. The heat and pressure from the sill cause the overlying rock to begin bulging upward in a process called doming. This doming occurs over thousands of years and creates a very gentle rise in the seafloor that might be only a few hundred feet high but extends for many miles across the ocean floor. The doming of the seafloor creates new zones of tension in the overlying rock. As the seafloor bulges upward, the rock layers are stretched and bent, creating fractures that radiate outward from the center of the dome. These radial fractures become potential pathways for magma to continue its upward journey, connecting the sill below with the rock layers closer to the seafloor. The sediment layer that covers the seafloor begins to show subtle signs of the activity below. In some areas, the sediments may be gently warmed by the heat rising from the magma sill below, creating very slight temperature anomalies that can be detected by sensitive instruments. In other areas, the upward bulging of the seafloor may create gentle slopes where sediments begin to slide slowly downward, redistributing the soft blanket that covers the ocean floor. The deep-sea life that inhabits this part of the ocean floor may begin to sense the subtle changes occurring below. Some organisms are sensitive to very small changes in temperature or chemical composition of the water near the seafloor. The heat rising from the developing magma sill may create very gentle convection currents in the bottom water, carrying slightly warmed water upward and creating a barely detectable change in the local environment. As the magma continues to accumulate in the sill and new fractures develop in the rock above, the stage is being set for the next major advance in the magma's journey toward the surface. The sill has served its purpose as a staging area and pressure accumulator, and now the focused pressure it has created begins to drive magma into the new fractures that lead upward toward the seafloor. The breakthrough from the sill into the overlying rock occurs through the same gentle process that characterized the original formation of the sill. Magma begins to seep into the most favorable fractures, gradually widening them through thermal and chemical action. These new intrusions start as hairline cracks filled with liquid rock, but they slowly grow wider and more substantial as more magma is fed into them from the sill below. The dikes that form above the sill are typically more direct and vertical than those that formed in the deeper parts of the system. This is because the pressure gradients are now more focused and the pathways to the surface are shorter and more clearly defined. The magma in these upper dikes moves with more purpose and direction, following the most efficient routes toward the seafloor above. As these upper dikes develop and begin to carry significant volumes of magma toward the surface, the thermal effects become more pronounced. The rock immediately surrounding the dikes is heated to temperatures that cause significant changes in its physical and chemical properties. These changes create a zone of altered rock around each dike that may be more susceptible to further fracturing and intrusion. The pressure in the upper part of the magma system begins to fluctuate as magma moves through the dikes toward the surface. When magma moves freely through the dikes, the pressure in the sill below decreases slightly. When the upward movement of magma is temporarily blocked by tighter sections of the dikes, pressure builds up again in the sill. These pressure fluctuations create a dynamic system that will eventually regulate the flow of magma to the surface. The chemical composition of the magma continues to evolve as it moves through the upper dikes. The interaction with different types of rock at different levels can create magmas with distinct chemical signatures. The cooling that occurs as magma moves toward the surface can cause different minerals to crystallize, further changing the composition of the liquid that will eventually reach the seafloor. As you rest there now, breathing slowly and deeply, you might imagine this gentle but significant breakthrough occurring far beneath some distant ocean. The first crack has formed, the first pathway has opened, and liquid rock is beginning its final approach toward the surface. The process remains patient and gradual, but momentum is building toward the moment when magma will finally reach the seafloor and begin the actual construction of a new island. The beauty of this breakthrough process lies in its inevitability and gentleness. There are no sudden ruptures or catastrophic failures. Instead, there's only the patient application of heat and pressure, the gradual yielding of rock to the inexorable forces rising from below. It's a process that demonstrates the way our Earth accomplishes its most dramatic transformations, not through violence or sudden change, but through the accumulated effect of countless small, incremental steps. The first gentle crack represents a threshold in the island-building process. Once magma has established a reliable pathway from the deep chambers to levels near the seafloor, the system becomes self-reinforcing. Each passage of magma widens the pathways and makes subsequent movement easier. The thermal effects of flowing magma weaken the surrounding rock and create new opportunities for intrusion. The pressure relief provided by the upward movement of magma allows new magma to be fed into the system from the deep chambers below. The dike system that extend from the seafloor down to the deep magma chambers now represents a complete plumbing system for volcanic activity, like the root system of a plant that will eventually grow above ground. This network of magma-filled fractures provides the infrastructure necessary to support the volcanic activity that will build the island above. The fracturing process that creates these pathways is also preparing the seafloor for the dramatic changes that are about to occur. The network of fractures that now extends throughout the crust beneath the seafloor creates zones of weakness that will influence how the volcanic activity expresses itself when it finally reaches the surface. Some fractures may become sites of sustained volcanic activity, while others may serve as pathways for hydrothermal circulation that will affect the chemistry of the overlying ocean water. As the magma system continues to develop and mature, the stage is set for the next phase of our story, the moment when liquid rock finally reaches the seafloor and begins to interact with the cold ocean water above. But that moment, when it comes, will be the natural culmination of all the patient processes we've been following, as inevitable and gentle as dawn breaking over a peaceful sea. The first gentle crack has opened the door to creation. The pressure that has been building for hundreds of thousands of years now has a pathway for release. The liquid rock that has been waiting in the deep chambers now has a route to the surface. The patient Earth has prepared the stage for the birth of new land, and the curtain is about to rise on one of nature's most magnificent performances, the emergence of an island from the depths of the sea. Now, as you rest there with an understanding of how the first pathways have opened from magma to approach the surface, let me take you to witness one of the most remarkable moments in our planet's creative process, the first contact between liquid rock and the cold ocean water far above. This meeting between fire and water, between the ancient heat of the Earth's interior and the patient coolness of the deep sea, marks the true beginning of an island's birth. Picture, if you will, the scene that unfolds 3 miles beneath the surface of the ocean, in a realm of eternal darkness, where the pressure is nearly 500 times greater than at the surface, and where the temperature of the water hovers just above freezing. Here, on the soft sediment floor of the abyssal plain, something unprecedented is about to occur. The first gentle emergence of molten rock from the seafloor, beginning the construction of what will eventually become a volcanic island. The magma that has been making its patient journey upward through the network of dikes and sills has finally reached the seafloor. The last few hundred feet of its ascent have been the most challenging, as the magma encounters the cold, wet environment near the seafloor where temperatures drop dramatically and the rock becomes saturated with seawater that has percolated down through fractures over millions of years. The moment when magma first contacts the seafloor is surprisingly gentle. There is no explosive breakthrough or violent eruption. Instead, the hot liquid rock begins to seep through the sediment layers like a warm spring emerging from ground. The temperature differential between the magma, at nearly 2,000 degrees Fahrenheit, and the surrounding environment, at just above freezing, creates an immediate and dramatic transformation. As the first droplets of magma encounter the cold seawater, they undergo an almost instantaneous change. The extreme temperature difference causes the outer surface of the magma to solidify immediately, forming a thin skin of solid rock around the still liquid interior. This process, called quenching, creates a protective shell that allows the magma to continue flowing while gradually cooling from the outside in. The interaction between hot magma and cold seawater creates a unique type of volcanic formation called pillow lava. As each blob of magma emerges from the seafloor, it forms a bulbous, pillow-like shape as its outer surface cools and hardens while the interior remains fluid. These pillows typically range from a few inches to several feet in diameter, and they stack and pile upon each other as more magma emerges from below. The formation of pillow lavas is one of the most characteristic features of underwater volcanic activity. Each pillow represents a separate pulse of magma emerging from the seafloor, cooling rapidly in the seawater, and then being covered by the next pillow to emerge. Over time, these pillows accumulate to form substantial mounds of volcanic rock, creating the first solid foundation upon which the future island will be built. The cooling process that creates pillow lavas is remarkably efficient. The cold seawater conducts heat away from the magma so quickly that even though the interior of each pillow may remain molten for hours or even days, the outer shell forms within seconds of contact with the water. This rapid cooling preserves the shape of each pillow and prevents the magma from spreading out into thin sheets that would cool too quickly to build substantial thickness. As the pillow lavas accumulate, they create a complex, three-dimensional structure that is unlike any terrestrial volcanic formation. The spaces between the pillows are filled with seawater, creating a porous network that allows water to circulate throughout the growing volcanic pile. This circulation of seawater through the hot volcanic rock creates a natural cooling system that helps to regulate the temperature of the entire structure. The interaction between the hot volcanic rock and the circulating seawater also creates unique chemical environments. The heated seawater becomes enriched in dissolved minerals leached from the fresh volcanic rock, creating hydrothermal fluids that are rich in elements like silica, sulfur, and various metals. These heated, mineral-rich waters rise through the porous volcanic pile and eventually emerge at the seafloor as hydrothermal vents. These early hydrothermal vents are the precursors to the more dramatic hot springs and geysers that may eventually characterize mature volcanic islands. At this early stage, they are gentle features that release warm, mineral-rich water into the cold, deep ocean. The temperature of this hydrothermal fluid is typically much lower than the original magma temperature, perhaps 100 to 300 degrees Fahrenheit, but still dramatically warmer than the surrounding seawater. The emergence of these hydrothermal vents marks the beginning of the first ecosystem associated with the growing volcanic pile. Deep-sea organisms that are adapted to hydrothermal environments begin to colonize the area around the vents, drawn by the warmth and the unique chemistry of the hydrothermal fluids. These organisms, primarily bacteria and archaea, form the base of a food web that will eventually support more complex life forms. The bacterial communities that establish themselves around these early hydrothermal vents are remarkable organisms that derive their energy not from sunlight, which never reaches these depths, but from chemical reactions involving the dissolved minerals in the hydrothermal fluids. This process, called chemosynthesis, allows these organisms to convert the chemical energy in the hydrothermal fluids into biological energy, creating the first living communities associated with the growing volcanic structure. As the pillow lava formation continues, the growing volcanopile begins to influence the local seafloor environment in increasingly noticeable ways. The accumulating volcanic rock creates topographic relief on what was previously a flat abyssal plain, generating the first hills and ridges that will eventually grow into the mountainous structure of a volcanic island. The weight of the accumulating volcanic rock also begins to affect the underlying seafloor. The soft sediments that have been accumulating on the ocean floor for millions of years are gradually compressed and displaced by the growing load of volcanic material. This process, called sediment loading, causes the seafloor to subside slightly under the weight of the volcanic pile, creating a gentle depression around the base of the growing volcanic structure. The rate at which pillow lavas accumulate depends on many factors, including the rate of magma supply from the deep chambers, the efficiency of the dike system in transporting magma to the surface, and the local conditions at the seafloor. In some cases, pillow lavas may accumulate at rates of several feet per year. In others, the process may be much slower, with significant accumulation occurring only over thousands of years. The composition of the pillow lavas reflects the chemistry of the magma that formed them, which in turn reflects the composition of the mantle source region and the processes that occur during the magma's journey to the surface. Most pillow lavas are basaltic in composition, meaning they are rich in iron and magnesium and relatively poor in silica. This composition gives them their characteristic dark color and dense texture. As the pillow lava pile grows in height and extent, it begins to create its own local environment that influences subsequent volcanic activity. The growing pile of volcanic rock creates thermal insulation that helps to keep the underlying magma pathways warm and active. The topographic relief created by the pile influences the local circulation of seawater, which in turn affects the cooling rate of new pillow lavas. The structure of the pillow lava pile is not uniform throughout its extent. Areas directly above the main magma conduits tend to accumulate pillow lavas more rapidly and to greater thickness than areas at the margins of the volcanic field. This differential accumulation creates a domical structure with the highest elevations near the center of the volcanic activity and lower elevations toward the margins. The internal structure of the pillow lava pile is complex and heterogeneous. The spaces between individual pillows create a network of voids that may be filled with seawater, sediment, or later volcanic material. Some of these voids may become pathways for hydrothermal circulation, while others may be sealed off by later volcanic activity or by the precipitation of minerals from hydrothermal fluids. As the pillow lava pile continues to grow, it reaches a critical threshold where its top approaches the depth where the pressure of the overlying seawater begins to significantly affect volcanic processes. At depths of less than about 1 mile below sea level, the reduced pressure allows dissolved gases in the magma to begin forming bubbles, which changes the character of the volcanic activity and marks the beginning of the transition toward more explosive volcanic processes. The growing volcanic pile also begins to influence the regional geological structure of the seafloor. The heat and pressure associated with the volcanic activity can reactivate old faults and fractures in the surrounding seafloor, creating pathways for additional volcanic activity. The thermal expansion of the rock around the volcanic pile can create new fractures that may become sites for future volcanic vents. The chemical alteration of the seafloor around the growing volcanic pile creates zones of rock with different physical and chemical properties than the original oceanic crust. This alteration is caused by the circulation of hot, chemically reactive fluids through the rock, which can dissolve some minerals and precipitate others. The altered rock may be either stronger or weaker than the original rock, depending on the specific chemical changes that occur. As you rest there now, breathing slowly and peacefully, you might imagine this remarkable scene unfolding far beneath some distant ocean. The seafloor, which has been quiet and stable for millions of years, is now experiencing the gentle birth of new volcanic features. Pillow lavas are accumulating one by one, slowly building the foundation of what will eventually become a volcanic island. The process we're witnessing represents one of the most fundamental ways that our planet creates new land. The same process that is forming pillow lavas on the deep ocean floor today has been operating for billions of years, creating much of the oceanic crust that covers the majority of our planet's surface. Every mid-ocean ridge, every underwater volcano, every place where new oceanic crust is formed follows similar processes of underwater magma eruption and pillow lava formation. The beauty of this process lies in its persistence and gradual nature. There are no sudden dramatic changes or violent explosions at these depths. Instead, there's only the patient accumulation of volcanic rock, pillow by pillow, layer by layer, slowly building the foundation for the island that will eventually rise above the waves. The pillow lavas that are forming now will become the basement rock of the future island, the solid foundation upon which all subsequent volcanic activity will build. These early volcanic rocks will eventually be buried beneath thousands of feet of additional volcanic material, but they will remain as the permanent record of the island's birth from the abyss. The hydrothermal systems that are developing around the growing pillow lava pile will continue to evolve as the volcanic activity progresses. Some hydrothermal vents may become long-lived features that persist for thousands of years, while others may be active for only brief periods before being covered by new volcanic material or sealed off by mineral precipitation. The ecosystems that are beginning to establish themselves around the hydrothermal vents represent the first life to colonize the growing volcanic structure. These communities will evolve and change as the volcanic environment changes, eventually giving way to different types of ecosystems as the volcanic pile grows upward toward the surface and the environmental conditions change. The regional geological effects of the growing volcanic pile will continue to influence seafloor processes for millions of years. The thermal and mechanical stresses created by the volcanic activity will create patterns of fracturing and faulting that may influence the location and character of future volcanic activity. The chemical alteration of the seafloor will create zones of rock with different properties that may affect how the region responds to future geological processes. As the pillow lava pile continues to grow and evolve, it approaches the next major milestone in the island building process, the point where the volcanic activity begins to build substantial topographic relief that significantly influences local ocean circulation and begins to create the mountainous structure that will eventually support terrestrial ecosystems. The birth from the abyss that we've been following represents the humble beginning of what may eventually become a substantial volcanic island. The first pillow lavas, forming quietly in the darkness of the deep ocean, carry within them the potential for mountains, valleys, forests, and all the complex landscapes that characterize mature volcanic islands. The process continues with the same patient persistence that has characterized every step of the island building process. Each new pillow lava adds to the growing pile. Each circulation of hydrothermal fluid alters the chemical composition of the volcanic rock. Each small change in the local environment influences the direction of future volcanic activity. The Earth works its slow magic, creating beauty and complexity from the simple interaction between molten rock and seawater. And in this ongoing process of creation, we can find a profound sense of peace and wonder. The same forces that are quietly building new islands in the depths of our oceans are part of the same planetary processes that have shaped our world throughout its history. We are witnessing not just the birth of a volcanic island, but the continuation of the creative forces that have made our planet the dynamic, living world that it is today. Now, as you rest there with an understanding of how the first volcanic structures have begun to form on the deep seafloor, let me take you on a journey through the patient centuries and millennia as these underwater mountains grow steadily upward, reaching ever closer to the distant sunlight that filters down through miles of ocean water. This is the story of persistence and gradual accumulation, where each day's volcanic activity adds another small increment to what will eventually become a substantial underwater mountain. Picture, if you will, the volcanic pile that has been growing on the seafloor for perhaps 10,000 years since the first pillow lavas began to form. What started as a small mound of volcanic rock on the abyssal plain has now grown into a substantial hill, rising perhaps 1,000 feet above the surrounding seafloor. The structure is no longer just a pile of individual pillow lavas, but has evolved into a complex volcanic edifice with its own internal architecture and its own influence on the surrounding ocean environment. The growth of this underwater volcano follows patterns that are both predictable and beautifully complex. The central area, where the main magma conduits reach the seafloor, continues to be the most active site of volcanic activity. Here, new pillow lavas are added almost continuously, though the rate varies depending on the supply of magma from the deep chambers below and the efficiency of the conduit system that brings magma to the surface. As the volcanic pile grows higher, the character of the volcanic activity begins to change in subtle but important ways. The reduced pressure at the higher elevations of the volcanic pile allows dissolved gases in the magma to expand more readily, creating magma that is slightly more vesicular, filled with tiny gas bubbles that make the resulting rock lighter and more porous than the dense pillow lavas that formed at greater depths. This change in the character of the volcanic rock has important implications for the structure and growth of the volcanic pile. The more vesicular rocks are less dense than the earlier pillow lavas, which means they can be built to greater heights before the volcanic pile becomes unstable. The increased porosity also allows for more efficient circulation of hydrothermal fluids through the volcanic pile, which affects both the cooling rate of new volcanic material and the development of hydrothermal systems. The hydrothermal systems that began to develop during the early stages of volcanic activity have now evolved into complex networks of hot springs and fluid circulation patterns. The growing height of the volcanic pile creates greater pressure differences between the base and the top of the structure, which drives more vigorous circulation of hydrothermal fluids. This enhanced circulation creates more efficient cooling of the volcanic pile and more extensive chemical alteration of the volcanic rocks. The hydrothermal vents that emerge at the seafloor around the volcanic pile have become more numerous and more diverse in their characteristics. Some vents emit relatively cool water, only slightly warmer than the surrounding seawater. Others discharge fluids at temperatures of several hundred degrees Fahrenheit, creating dramatic plumes of heated water that rise through the cold ocean like underwater geysers. The chemistry of the hydrothermal fluids has also become more complex as the fluids interact with the growing volume of volcanic rock in the pile. The fluids now carry a rich cocktail of dissolved minerals, including silica, sulfides of various metals, and exotic compounds that are rare in normal seawater. When these heated, mineral-rich fluids mix with the cold seawater, they precipitate various minerals, creating colorful deposits around the hydrothermal vents. These mineral deposits, known as hydrothermal precipitates, create some of the most visually striking features of the underwater volcanic environment. Tall chimneys of deposited minerals grow around some vents, creating structures that can reach heights of several tens of feet. These chimneys are often brightly colored, with hues ranging from brilliant white and yellow to deep orange and black, depending on the specific minerals being deposited. The ecosystem around the growing volcanic pile has also evolved and diversified as the hydrothermal systems have become more complex. The bacterial and archaeal communities that first colonized the area have been joined by more complex organisms that can take advantage of the diverse chemical environments created by the hydrothermal activity. Tube worms, clams, and other organisms that are specially adapted to hydrothermal environments have established thriving communities around the vents. These hydrothermal ecosystems represent some of the most unique biological communities on Earth. Unlike surface ecosystems that depend ultimately on energy from the sun, these communities derive their energy entirely from chemical processes powered by the heat of the Earth's interior. The organisms that live here have evolved remarkable adaptations that allow them to thrive in environments that would be instantly lethal to most surface organisms. The growing volcanic pile has also begun to influence ocean circulation patterns in the surrounding area. The substantial topographic relief created by the volcanic structure deflects deep ocean currents, creating complex patterns of water flow around and over the volcanic pile. These altered circulation patterns affect the distribution of nutrients and heat in the surrounding ocean, creating environmental gradients that influence the distribution of marine life. The sediment accumulation patterns around the volcanic pile have also changed as the structure has grown. The slopes of the volcanic pile create environments where different types of sediments accumulate at different rates. Fine sediments may be swept away from the steep slopes near the volcanic vents, while they accumulate in thicker layers in the quieter areas between volcanic features. As the volcanic pile continues to grow, it begins to develop more complex internal structures. The continuous accumulation of volcanic material creates layers within the pile that record the history of volcanic activity. Periods of more intense activity are recorded as thicker layers of volcanic rock, while quieter periods are recorded as thinner layers or as intervals where hydrothermal alteration has modified the volcanic rocks. The internal structure of the volcanic pile is also affected by the intrusion of new magma into the existing volcanic material. As magma continues to rise from the deep chambers, some of it may not reach the surface but instead intrudes into the existing volcanic pile, creating sills and dikes within the structure. These intrusions add to the total volume of the volcanic pile and can also influence the direction and character of future volcanic activity. The mechanical stability of the growing volcanic pile becomes an increasingly important factor as the structure grows larger. The soft sediments of the deep seafloor can only support a limited amount of weight before they begin to deform or subside. As the volcanic pile grows, it causes increasing subsidence of the underlying seafloor, which affects the overall shape and growth pattern of the volcanic structure. The growing volcanic pile also begins to generate its own local gravitational field, which becomes measurable when the structure reaches substantial size. This gravitational anomaly can influence the flow patterns of magma in the conduits below the volcanic pile and can also affect the local stress field in the surrounding seafloor, potentially creating new fractures that could become sites for future volcanic activity. As the volcanic structure approaches heights of several thousand feet above the surrounding seafloor, it begins to enter depth ranges where the pressure of the overlying seawater has less influence on volcanic processes. At depths of less than about 3,000 feet below sea level, dissolved gases and magma can begin to form significant bubbles, which changes the character of volcanic eruptions and marks the beginning of the transition toward more explosive volcanic activity. The growth rate of the volcanic pile is not constant but varies depending on many factors, including the rate of magma supply from the deep chambers, the efficiency of the conduit system, and the local geological conditions. During periods of high magma supply, the volcanic pile may grow rapidly, adding hundreds of feet of new volcanic material in just a few years. During quieter periods, growth may be much slower, with significant accumulation occurring only over thousands of years. The chemical composition of the volcanic rocks continues to evolve as the volcanic pile grows and the magma system matures. The interaction between magma and seawater becomes more complex as the volcanic pile grows larger, creating opportunities for more extensive chemical exchange between the magma and the surrounding environment. The magma may also undergo more extensive cooling and crystallization during its journey through the larger volcanic pile, which can change its composition and properties. The development of the volcanic pile is also influenced by external factors such as changes in sea level, variations in the rate of magma supply from the deep mantle, and regional geological processes. These external influences can cause changes in the growth rate and character of the volcanic pile that are recorded in its internal structure and can be detected by careful geological study. As you rest there now, breathing slowly and deeply, you might imagine this remarkable process of growth occurring over thousands of years beneath some distant ocean. The volcanic pile, invisible to human eyes but growing steadily day by day, represents one of the most patient and persistent creative processes on our planet. Each new layer of volcanic rock, each circulation of hydrothermal fluid, each small change in the ecosystem represents a step in a long journey toward the creation of a new island. The timescales involved in this growth process are vast, often spanning tens or hundreds of thousands of years. The volcanic pile that will eventually become a surface island might take longer to grow than humans have existed as a species. Yet the process continues with unwavering persistence, driven by the fundamental forces that power our planet's geological activity. The beauty of this underwater mountain-building process lies in its systematic and patient nature. There are no sudden dramatic changes or catastrophic events. Instead, there's only the steady accumulation of volcanic material, the gradual building of topographic relief, the slow evolution of hydrothermal systems and ecosystems. It's a process that exemplifies the way our planet accomplishes its most remarkable transformations through the accumulated effect of countless small, incremental changes. The volcanic pile growing toward the light represents more than just a geological structure. It represents the Earth's creative potential made manifest. Each layer of volcanic rock carries within it the chemical signature of the deep Earth, brought to the surface through processes that connect the deepest parts of our planet with a life-sustaining ocean above. The growing volcanic structure also serves as a bridge between different realms of our planet. It connects the deep, hot interior of the Earth with the cold, life-filled ocean above. It creates environments where chemical energy from the Earth's interior can support biological communities that exist nowhere else. It demonstrates the fundamental interconnectedness of all Earth systems, from the deepest mantle to the ocean surface. As the volcanic pile continues its patient growth toward the distant surface, it carries with it the potential for even more remarkable transformations. The underwater mountain that is growing steadily toward the light will eventually reach depths where sunlight can penetrate, where different types of marine life can flourish, and where the character of volcanic activity will change dramatically as the structure approaches the surface. The journey toward the light is not just a physical journey through the water column, but also a journey through different environmental zones, each with its own characteristics and challenges. As the volcanic pile grows upward, it will encounter different pressures, different temperatures, different chemical conditions, and different biological communities. Each zone will leave its mark on the growing structure, creating a complex record of the volcano's journey from the deep seafloor toward the surface. The hydrothermal systems that have developed around the growing volcanopile will also continue to evolve as the structure grows toward the surface. The changing pressure conditions will affect the behavior of hydrothermal fluids, potentially creating new types of vents and new patterns of mineral deposition. The evolving ecosystem will create new opportunities for biological-geological interactions that may influence the development of the volcanic structure. The growing volcanic pile represents a work in progress, a dynamic system that is constantly changing and evolving as it builds toward its ultimate goal of reaching the ocean surface. Every day brings new additions to the structure, new changes in the hydrothermal systems, new developments in the associated ecosystems. The volcanic pile is not just growing in size, but growing in complexity, developing the internal architecture and external features that will eventually characterize it as a mature volcanic island. And as this underwater mountain continues its patient journey toward the light, it reminds us of the remarkable persistence and creativity of our living planet. The same forces that are building this volcanic pile are at work throughout our oceans, constantly creating new seafloor, new volcanic features, new opportunities for life. The Earth never stops creating, never stops building, never stops reaching toward new possibilities for beauty and complexity. The volcanic pile growing toward the light is a testament to the power of patience and persistence. It demonstrates that the most remarkable achievements often come not through sudden dramatic action, but through the steady accumulation of small, consistent efforts over vast periods of time. In this gentle building process, we can find inspiration for our own lives and comfort in the knowledge that we are part of a planet that never stops creating beauty and wonder. Now, as you rest there with an understanding of how underwater volcanic mountains grow patiently toward the surface, let me take you to witness one of the most remarkable moments in the life of a volcanic island. The first time that molten rock breaks through the ocean surface and encounters the atmosphere above. This transition from underwater to surface volcanic activity marks a profound change in the character of the volcanic processes and the beginning of true land formation. Picture, if you will, the underwater volcanic mountain that has been growing for perhaps 100,000 years, slowly building its mass layer by layer, eruption by eruption, from the deep seafloor toward the distant surface. The mountain now rises nearly 2 miles above the surrounding seafloor, its summit approaching the critical depth of about 500 feet below sea level. The zone where the reduced pressure of the overlying water begins to dramatically change the behavior of volcanic eruptions. At these shallow depths, the volcanic processes we've been following begin to undergo a remarkable transformation. The magma that has been forming pillow lavas in the deep ocean now encounters pressure conditions that allow dissolved gases to expand much more readily. Water vapor, carbon dioxide, and other gases that have been dissolved in the magma under high pressure begin to form bubbles as the magma rises to these shallower depths. The formation of gas bubbles in the ascending magma creates what geologists call vesicular lava, volcanic rock that is filled with countless tiny holes where gas bubbles were trapped as the lava cooled. This vesicular character makes the lava lighter and more buoyant than the dense pillow lavas that formed in the deep ocean, allowing the volcanic mountain to build more efficiently toward the surface. As the summit of the underwater volcano approaches depths of 200 to 300 feet below sea level, the character of the eruptions begins to change more dramatically. The expanding gases in the magma create enough pressure to fragment the lava into smaller pieces, creating underwater eruptions that produce volcanic bombs, lapilli, and volcanic ash instead of the coherent pillow lavas that characterize deeper eruptions. These shallow underwater eruptions create deposits called hyaloclastite, a mixture of volcanic glass fragments, crystals, and ash that forms when magma is rapidly quenched and fragmented by contact with seawater. The hyaloclastite deposits accumulate around the volcanic vents, creating broad, cone-shaped structures that build the final approaches to the ocean surface. The interaction between the fragmenting magma and the seawater at these shallow depths creates spectacular underwater displays that would be breathtaking to witness if we could observe them directly. Steam and gas bubbles rise through the water column in great plumes, carrying with them fragments of volcanic glass that glitter like black diamonds in the blue-green light that filters down from the surface. The marine life in the vicinity of these shallow volcanic eruptions experiences dramatic changes in their environment. The water temperature may fluctuate significantly as hot volcanic material mixes with cold seawater. The chemistry of the seawater changes as volcanic gases and dissolved minerals are added to the water column. Some marine organisms may be displaced by these changes, while others that are adapted to dynamic environments may thrive in the constantly changing conditions. As the volcanic mountain continues to build upward through this zone of shallow water eruptions, it approaches the most critical threshold in its development. The depth at which the top of the volcano is close enough to the surface that wave action begins to affect the volcanic processes. At depths of less than about 100 feet, the orbital motion of waves begins to create significant water movement at the seafloor, which can influence the direction of volcanic eruptions and the accumulation of volcanic debris. The moment when a volcanic eruption first breaks through the ocean surface is one of the most dramatic transitions in all of geology. The eruption, which has been constrained by the surrounding water throughout its underwater phase, suddenly encounters the very different environment of the atmosphere above the ocean. The result is often an explosion of steam as the hot volcanic material instantly vaporizes large quantities of seawater. The first surface eruptions of a new volcanic island are typically highly explosive events, driven by the violent interaction between molten lava and seawater. This interaction, called a Surtsian eruption after the famous 1963 emergence of Surtsey Island off the coast of Iceland, creates towering columns of steam, ash, and volcanic bombs that can rise thousands of feet into the air above the ocean surface. Despite their explosive character, these initial surface eruptions follow the same patient, systematic patterns that have characterized the entire island-building process. The eruptions occur in pulses, with periods of intense activity alternating with quieter intervals. Each eruption adds new volcanic material to the growing structure, gradually building the solid foundation that will support the permanent emergence of new land above sea level. The steam columns that rise from these early surface eruptions are visible from great distances, often appearing as towering clouds that dwarf even the largest thunderstorms. These steam columns are composed primarily of water vapor created by the vaporization of seawater, mixed with volcanic gases and fine particles of volcanic ash. The columns can reach heights of 30,000 feet or more, creating spectacular displays that announce the birth of new land to anyone who might be watching from a great distance. The ash and volcanic debris from these eruptions falls over a wide area around the emerging volcano, creating a rain of volcanic material that can extend for hundreds of miles downwind from the eruption site. This volcanic ash, composed of tiny fragments of volcanic glass and crystals, settles onto the ocean surface and eventually sinks through the water column to accumulate on the seafloor, creating a geological record of the island's emergence that can be studied by scientists long after the eruptions have ended. The first solid land to emerge above sea level is typically a small, irregularly shaped island composed of volcanic debris and solidified lava. This initial island is often unstable, built up quickly during intense eruptive episodes, and then partially eroded away by wave action during quieter periods. The battle between volcanic construction and marine erosion becomes a defining characteristic of the island's early development. The waves that crash against the emerging volcanic island are incredibly powerful erosive forces. The volcanic rocks that form during these early stages are often relatively soft and porous, making them susceptible to rapid erosion by wave action. Large chunks of the newly formed island may be broken off and carried away by storms, requiring continuous volcanic activity to maintain and expand the island's surface area. The chemistry of the seawater around the emerging island becomes dramatically altered during the intense volcanic activity. The water may become acidic from dissolved volcanic gases, and it becomes heavily laden with suspended volcanoparticles that can turn the sea a distinctive gray or brown color for miles around the island. The temperature of the seawater may also be elevated over a large area due to the heat released by the volcanic activity. As the volcanic island continues to grow and erupt, it begins to establish a more stable foundation above sea level. The accumulation of volcanic debris and the gradual solidification of lava flows create a more substantial landmass that is better able to withstand the erosive power of ocean waves. The island begins to develop a characteristic shape, typically conical or elongated depending on the pattern of volcanic vents and the direction of prevailing winds and currents. The early surface volcanic activity creates a variety of different types of volcanic rocks and deposits. Lava flows that reach the surface and flow into the ocean create distinctive formations where the hot lava meets the cold seawater. These formations, called pilobreccias or hyaloclastite deltas, have a characteristic structure that records the interaction between flowing lava and seawater. The explosive eruptions that characterize the early surface activity also create distinctive volcanic landforms. Cinder cones, formed by the accumulation of volcanic bombs and lapilli around eruption vents, become prominent features of the emerging island. Tuff rings, formed by the accumulation of fine volcanic ash, create broad, low structures that can cover large areas of the island's surface. The atmospheric conditions around the emerging island are dramatically affected by the volcanic activity. The large quantities of water vapor and volcanic gases released during eruptions can create local weather patterns that are quite different from the normal oceanic climate. The area around the island may experience frequent rain showers as the water vapor in the volcanic plumes condenses and falls as precipitation. The volcanic gases released during the surface eruptions include not only water vapor, but also carbon dioxide, sulfur dioxide, and other compounds that can affect air quality over a large area around the island. While these gases are typically diluted to safe levels by atmospheric mixing, they can create distinctive odors and atmospheric effects that extend for many miles from the island. As you rest there now, breathing slowly and peacefully, you might imagine this dramatic moment of emergence occurring somewhere in the vast ocean. After hundreds of thousands of years of patient underwater growth, molten rock finally breaks through the ocean surface and begins to build the first solid land above sea level. The process is both explosive and creative, destructive and constructive, representing the Earth's remarkable ability to create new landscapes through the interaction of fundamental geological forces. The breaking of the surface represents not just a physical breakthrough, but a transition between different realms of Earth systems. The volcanic processes that have been operating in the hidden depths of the ocean are now interacting with the atmosphere, with weather patterns, with solar radiation, and with all the complex systems that characterize the surface environment of our planet. The emergence of new land above sea level also marks the beginning of opportunities for terrestrial life to colonize the volcanic island. While the initial environment is harsh and constantly changing due to ongoing volcanic activity, it represents new habitat that will eventually be colonized by plants, animals, and microorganisms that will transform the barren volcanic rock into complex ecosystems. The first plants to reach the emerging island will likely be carried by wind or ocean currents from distant lands. Salt-tolerant plants that can survive in the harsh conditions near the ocean shore will be among the first to establish themselves on the new land. These pioneer species will begin the long process of soil formation and ecosystem development that will eventually transform the volcanic island into a complex landscape capable of supporting diverse communities of life. The surface volcanic activity that accompanies the island's emergence also creates the geological foundation for the island's future development. The lava flows, ash deposits, and other volcanic features that form during this critical period will determine the basic topography and geology of the island. The drainage patterns that develop as rainwater begins to flow across the volcanic landscape will carve the valleys and ridges that will characterize the island's mature topography. The breaking of the surface is also the moment when the volcanic island becomes visible to any passing ships or aircraft, officially marking its existence as a new piece of land on the Earth's surface. This moment of recognition often marks the beginning of human interest in the island, though it may be many years before the volcanic activity subsides enough to allow safe human exploration. The continued volcanic activity following the initial surface breakthrough is crucial for the island's survival and growth. The volcanic processes must continue to add new material to the island faster than wave erosion can remove it. This balance between construction and destruction will determine whether the emerging island will grow into a substantial landmass or will be eroded away and disappear beneath the waves. The character of the volcanic activity may change as the island grows larger and more stable above sea level. The explosive Circean eruptions that characterize the initial emergence may give way to more effusive lava flows as the volcanic system matures and the influence of seawater on the eruptions decreases. These changes in volcanic style will affect the types of rocks that form and the shape of the growing island. The breaking of the surface represents a triumph of geological persistence over oceanic forces. The patient accumulation of volcanic material over hundreds of thousands of years has finally overcome the tremendous obstacles presented by miles of overlying seawater and the erosive power of ocean waves. The emergence of new land above sea level demonstrates the remarkable creative power of our planet's internal heat and energy. As the newly emerged island continues to grow and evolve, it embarks on the next phase of its development. The establishment of permanent land above sea level and the beginning of the complex processes that will transform barren volcanic rock into the rich, diverse landscapes that characterize mature volcanic islands. The breaking of the surface is not an ending, but a beginning, the start of a new chapter in the island's long journey toward becoming a fully developed piece of our planet's land surface. Now, as you rest there with an understanding of how volcanic mountains break through the ocean surface, let me take you through the patient process by which these newly emerged volcanic features transform themselves into permanent, stable islands. This is the story of how raw volcanic material, forged in the Earth's deep fires and thrust above the waves, gradually becomes solid land capable of supporting the weight of mountains, the flow of rivers, and eventually the complex web of life itself. Picture, if you will, the scene several months after the first explosive breakthrough of volcanic material above the ocean surface. The initial dramatic eruptions have subsided into a more steady rhythm of volcanic activity, and what was once just a temporary mound of loose volcanic debris is beginning to solidify into something more substantial and permanent. The island, perhaps only a few hundred yards across at this early stage, rises modestly above the waves, its dark volcanic rocks glistening with spray from the constant crash of ocean swells. The volcanic activity that now characterizes the emerging island has settled into a pattern that favors construction over destruction. The explosive Circean eruptions that marked the initial surface breakthrough have given way to more effusive activity. Lava flows that pour steadily from volcanic vents and spread across the island's surface, creating solid rock foundations that are much more resistant to erosion than the loose volcanic debris of the early emergence phase. These lava flows represent the beginning of the island's transformation from a temporary accumulation of volcanic fragments into a permanent geological structure. As the molten rock emerges from volcanic vents, it spreads across the irregular surface of the early volcanic deposits, filling in low areas and creating increasingly smooth and stable surfaces. The lava, cooling in the open air rather than in the quenching environment of seawater, forms dense, solid rock that provides a much more durable foundation for future volcanic activity. The cooling process of these early lava flows creates some of the most characteristic features of young volcanic islands. As the molten rock cools and contracts, it often develops a distinctive pattern of cooling joints, regular fractures that divide the cooling lava into geometric blocks. These cooling joints give the solidified lava flows their characteristic appearance and also create zones of weakness that will influence future erosion patterns and the development of the island's topography. The surface of the cooling lava flows develops distinctive textures depending on the specific conditions under which the lava cooled. Lava that cools relatively slowly may develop a smooth, ropey texture called pahoehoe, characterized by undulating surfaces that look like frozen ropes or coils. Lava that cools more quickly, or that contains more gas bubbles, may develop a rough, clinker-like texture called AA, characterized by sharp, angular fragments that create challenging terrain for any future visitors to the island. As successive lava flows accumulate on the island's surface, they begin to build substantial topographic relief. Each new flow follows the topography created by previous flows, generally moving downslope toward the ocean and filling in the lowest areas first. Over time, this process creates a layered structure within the island, with each lava flow representing a distinct episode in the island's volcanic history. The interaction between new lava flows and the ocean creates some of the most dynamic and visually spectacular aspects of the island building process. When hot lava flows reach the ocean, they create dramatic displays of steam and turbulent water as the molten rock is rapidly quenched by contact with seawater. These lava-ocean interactions, called ocean entries, create new land at the edge of the island while also creating distinctive rock formations at the boundary between land and sea. The rock formations created by lava-ocean interactions are both beautiful and geologically significant. The rapid cooling of lava in seawater creates volcanic glass and distinctive pillow-like structures at the water's edge. The steam created by the interaction can carry volcanic particles high into the air, where they settle to create layers of volcanic sand and ash around the margins of the island. The ocean entries also create opportunities for the island to expand its surface area. As lava flows enter the ocean and cool, they create new solid ground that extends the island shoreline. This process, called progradation, allows the island to grow not just upward through continued volcanic activity, but also outward by claiming new territory from the sea. The development of a stable shoreline is crucial for the island's long-term survival. The constant battle between volcanic construction and wave erosion that characterizes the early stages of island emergence gradually shifts in favor of construction as more solid lava flows create erosion-resistant coastlines. The development of sea cliffs, where solid lava flows meet the ocean, creates natural barriers that protect the interior of the island from the most severe wave erosion. As the island grows larger and more stable, it begins to influence local weather patterns in ways that have profound implications for its future development. The solid rock of the island absorbs solar radiation during the day and releases heat at night, creating temperature differences that drive local air circulation patterns. These circulation patterns can influence cloud formation and precipitation, beginning the hydrological processes that will eventually carve the island's valleys and ridges. The first rainfall on the new island marks the beginning of chemical weathering processes that will gradually transform the fresh volcanic rock into soil. Rainwater, slightly acidic from dissolved carbon dioxide in the atmosphere, begins to react with the volcanic minerals, slowly dissolving some components and altering others. This chemical weathering is the first step in the long process that will eventually create the fertile soils necessary to support plant life. The drainage patterns that develop as rainwater flows across the island surface are strongly influenced by the topography created by volcanic activity. Water naturally flows along the lowest areas between lava flows, gradually carving small channels that will eventually develop into the stream valleys that characterize mature volcanic islands. These early drainage patterns establish the basic framework for the island's future topographic development. The volcanic activity that continues to shape the growing island also creates a variety of different landforms and geological structures. Cinder cones, formed by the accumulation of volcanic fragments around point sources of eruption, create distinctive conical hills scattered across the island surface. These cones, typically a few hundred feet high, add topographic complexity to the island and create diverse microenvironments that will influence future ecological development. Lava tubes, formed when the surface of a lava flow cools and solidifies while molten lava continues to flow beneath, create extensive underground networks that add to the structural complexity of the island. These tubes can extend for miles beneath the island's surface, creating underground spaces that may later become important features for groundwater storage and movement. The chemical composition of the volcanic rocks being produced during this construction phase influences many aspects of the island's development. Basaltic lavas, which are typical of volcanic islands, are rich in iron and magnesium and relatively poor in silica. This composition affects the color, density, and weathering characteristics of the rocks, influencing everything from the island's appearance to the types of soils that will eventually develop. The gas content of the erupting lavas also affects the character of the volcanic rocks and landforms being created. Lavas with high gas content create vesicular rocks filled with bubble holes, which are lighter and more porous than dense, gas-poor lavas. The porosity of these rocks affects their strength, their permeability to water, and their susceptibility to weathering and erosion. As the island grows larger, it begins to develop internal structure that will influence its long-term stability and evolution. The repeated eruption of lava flows creates a layered structure within the island, with older flows buried beneath newer ones. This layering can create zones of different strength and permeability within the island that will influence future volcanic activity and erosion patterns. The heat generated by ongoing volcanic activity also affects the mechanical properties of the island's rocks. The repeated heating and cooling of volcanic rocks can create thermal stresses that contribute to fracturing and joint development. These fractures and joints become important pathways for groundwater movement and also influence the direction and pattern of future erosion. The growing island also begins to develop its own local gravitational field, which becomes measurable as the island reaches substantial size. This gravitational field can influence the flow of magma in the volcanic system below the island and can also affect ocean currents and atmospheric circulation patterns around the island. The electromagnetic properties of the island also change as it grows and develops. The iron-rich volcanic rocks create local magnetic anomalies that can be detected by sensitive instruments. These magnetic signatures provide information about the temperature and cooling history of the volcanic rocks and can be used to study the internal structure of the island. As you rest there now, breathing slowly and peacefully, you might imagine this remarkable construction process occurring over decades and centuries. The island, no longer just a temporary accumulation of volcanic debris, is becoming a permanent feature of the Earth's surface. Each new lava flow adds to its stability and complexity. Each interaction with the ocean expands its boundaries. Each rainfall begins the slow process of soil formation that will eventually support life. The timescales involved in this construction process are both human and geological. While individual lava flows may form in a matter of days or weeks, the overall construction of a stable volcanic island typically takes centuries to millennia. The island that emerges from this construction phase may be only a few miles across and a few hundred feet high, but it represents a solid foundation for the much larger and more complex island that will eventually develop. The beauty of this construction process lies in its systematic and additive nature. Each volcanic event builds upon the foundation created by previous events, gradually creating increasingly complex and stable structures. There are no wasted efforts or false starts. Every lava flow, every volcanic deposit, every interaction with the ocean contributes to the growing solidity and permanence of the emerging island. The island that is being created through this process is not just a geological structure, but the foundation for future ecosystems and landscapes. The topographic relief created by volcanic activity will channel the flow of air and water, creating diverse microenvironments that will influence the types of life that eventually colonize the island. The chemical composition of the volcanic rocks will determine the types of soils that develop and the nutrients available to support plant growth. The drainage patterns established during this construction phase will determine the locations of future valleys, streams, and watersheds. The orientation and shape of lava flows will influence the island's exposure to wind and weather, affecting local climate patterns and the distribution of precipitation. All of these factors will play crucial roles in determining what kinds of ecosystems can develop on the island. The construction process also creates the geological framework for the island's future evolution. The internal structure of layered lava flows creates zones of different strength and permeability that will influence how the island responds to future volcanic activity, earthquakes, and erosion. The fracture and joint patterns developed during cooling will become important pathways for groundwater flow and will also influence the development of cave systems and underground drainage. The shoreline features created during the construction phase will determine how the island interacts with ocean waves and currents for millions of years to come. The development of sea cliffs, beaches, and coastal platforms during this early period establishes the basic framework for the island's coastal evolution. These features will be modified by future volcanic activity and erosion, but the basic pattern established during the construction phase will continue to influence the island's coastal character. The volcanic vents and structures created during the construction phase also establish the locations for future volcanic activity. While new vents may develop anywhere on the island, there's often a tendency for volcanic activity to recur in the same general areas where successful eruptions have occurred before. This tendency creates the volcanic centers and chains that characterize many mature volcanic islands. The construction of new land through volcanic processes also represents one of the few ways that the Earth's land surface area can actually increase. While most geological processes involve the rearrangement or erosion of existing land, volcanic island formation creates entirely new land where none existed before. This process has been responsible for creating many of the world's most beautiful and ecologically important islands. The newly constructed island also becomes part of the global systems that govern ocean circulation, atmospheric patterns, and biological distribution. The island creates new obstacles and opportunities for ocean currents, potentially affecting the movement of marine life and the distribution of nutrients in the surrounding ocean. It creates new stepping stones for the dispersal of terrestrial organisms across ocean basins. As the construction phase gradually gives way to the next stage of island development, the foundation has been laid for all the remarkable transformations that will follow. The solid volcanic rock that has been created through this patient construction process will provide the stable platform necessary for the development of complex topography, diverse ecosystems, and all the intricate beauty that characterizes mature volcanic islands. The creating of new land through volcanic processes is one of the most fundamental and inspiring demonstrations of our planet's creative power. From the patient stirring in the deep mantle that we followed at the beginning of our journey, through the gradual building of pressure and the gentle breakthrough to the surface, we have now witnessed the actual creation of new land, solid, permanent, and ready to support the next chapters in the ongoing story of life on Earth. Now, as you rest there with an understanding of how volcanic processes create solid, permanent land above the ocean's surface, let me take you through the beautiful transformation that occurs as these newly formed islands develop their distinctive shapes and characteristic landscapes. This is the story of how raw volcanic foundations gradually evolve into the complex topographic features that will define the island's character for millions of years to come. Picture, if you will, the volcanic island several thousand years after its initial emergence, when the basic foundation of solid lava flows has been established and the ongoing volcanic activity has settled into patterns that favor the systematic construction of increasingly complex landforms. The island has grown from its humble beginnings as a small mound of volcanic debris into a substantial piece of land, perhaps several miles across and rising several hundred feet above sea level. The shape that the island develops during this critical period is strongly influenced by the pattern and style of volcanic activity that continues to build its mass. If the volcanic activity is concentrated at a single central vent, the island tends to develop the classic conical shape that we associate with volcanic mountains, a broad, gently sloping cone that rises symmetrically from the ocean on all sides. If the volcanic activity occurs along a linear zone of weakness, the island may develop an elongated shape, resembling a ridge or chain of connected volcanic hills. The slopes that develop on the growing island are determined by the angle of repose of the volcanic materials being deposited. Loose volcanic debris, such as cinder and volcanic bombs, can only maintain slopes of about 30 to 35 degrees before becoming unstable and sliding downhill. Lava flows, on the other hand, can create much steeper slopes, particularly if the lava is viscous and cools quickly. The interplay between these different types of volcanic deposits creates the complex slope profiles that characterize mature volcanic islands. As the island continues to grow, it develops an increasingly sophisticated internal drainage system. The irregular surface created by successive lava flows naturally creates depressions and channels where rainwater can collect and flow. These early drainage patterns are often radial, flowing outward from the central volcanic areas toward the ocean like the spokes of a wheel. Over time, these drainage channels deepen and extend, gradually carving the valley systems that will become permanent features of the island's topography. The formation of these early valleys represents the beginning of the long battle between volcanic construction and erosional destruction that will characterize the island throughout its geological life. While volcanic activity continues to build the island upward and outward, the forces of erosion, primarily running water, but also wind and wave action, begin the slow process of wearing down and reshaping the volcanic structures. The rate of erosion depends on many factors, including the climate of the island, the resistance of the volcanic rocks to weathering, and the steepness of the slopes. In tropical climates with abundant rainfall, erosion can be quite rapid, carving deep valleys in relatively soft volcanic rocks within just a few thousand years. In drier climates, the erosional processes are much slower, allowing volcanic structures to maintain their original forms for much longer periods. The volcanic activity that continues to shape the island also becomes more diverse and complex as the island matures. While the early stages of island formation are typically dominated by basaltic lava flows, the volcanic system may evolve to produce lavas with different chemical compositions and physical properties. More silica-rich lavas, which are more viscous and tend to form steeper-sided volcanic domes and flows, may begin to appear as the magma system becomes more differentiated through cooling and crystallization processes. The development of multiple volcanic vents across the island's surface creates a complex pattern of overlapping volcanic features. Some vents may remain active for thousands of years, building substantial volcanic cones or shield volcanoes. Others may be active for only brief periods, creating smaller features like spatter cones or short lava flows. The cumulative effect of all this volcanic activity is the creation of a topographically complex landscape with a rich variety of volcanic landforms. The interaction between ongoing volcanic activity and the developing drainage system creates some of the most dramatic topographic features of volcanic islands. When lava flows in counterstream valleys, they may dam the valleys, creating temporary lakes behind lava dams. When these dams are eventually breached by continuing stream flow or by a subsequent volcanic activity, they can create spectacular waterfalls and gorges that become permanent features of the island's landscape. The coastal features of the island also continue to evolve as volcanic activity interacts with marine processes. Lava flows that reach the ocean create new shoreline segments with distinctive characteristics. Some areas may develop rocky headlands where resistant lava flows meet the ocean, while other areas may develop beaches where volcanic debris has been broken down by wave action into sand and gravel. The development of coral reefs around the island's shoreline may also begin during this period, particularly if the island is located in tropical waters. Coral larvae, carried by ocean currents from distant reefs, may find suitable habitat in the clear, warm waters around the volcanic island. The growth of coral reefs adds another layer of complexity to the island's coastal environment and provides important protection from wave erosion. As you rest there now, breathing slowly and peacefully, you might imagine this complex shaping process occurring over thousands of years. The island, no longer just a simple mound of volcanic rock, is developing the intricate topography and diverse landscapes that will characterize it for the rest of its geological life. Each volcanic eruption, each rainstorm, each interaction between land and sea contributes to the island's evolving shape and character. The timescales involved in this shaping process are long enough to encompass many human generations, yet short enough to represent just a brief moment in geological time. The basic topographic framework of the island may be established within 10 to 20,000 years of its initial emergence, but the fine details of its landscape will continue to evolve for millions of years as volcanic activity wanes and erosional processes become more dominant. The beauty of this shaping process lies in the dynamic balance between construction and destruction, between the creative forces of volcanic activity and the sculpting forces of erosion. Neither process dominates completely. Instead, they work together to create landscapes of remarkable complexity and beauty. The volcanic activity provides the raw material and basic structure, while erosion carves the fine details and creates the diversity of environments that will eventually support complex ecosystems. Now, as you rest there with an understanding of how volcanic islands develop their characteristic landscapes, let me take you through one of the most remarkable chapters in the island's story, the gradual arrival and establishment of life on what was once barren volcanic rock. This is a tale of incredible persistence and adaptability as plants, animals, and microorganisms find ways to cross vast ocean distances and establish themselves in entirely new environments. Picture, if you will, the volcanic island several thousand years after its landscape has taken shape, when the ongoing volcanic activity has created a diverse topography of hills and valleys, cliffs and beaches, all sculpted from dark volcanic rock under the endless blue of the tropical sky. The island appears lifeless from a distance, its slopes covered only with the browns and grays of weathered volcanic material. Yet the stage is now set for one of nature's most beautiful transformations. The first colonists to reach the island are not plants or animals, but microscopic organisms carried by the wind across hundreds or thousands of miles of open ocean. Bacteria, fungal spores, and other microorganisms drift through the atmosphere like an invisible rain of life, settling onto every surface of the earth. Some of these microscopic travelers find conditions on the volcanic island suitable for survival and begin to establish the first biological communities on the new land. These pioneering microorganisms play a crucial role in preparing the island for more complex forms of life. Bacteria that can derive energy from chemical reactions begin to break down the volcanic rock, extracting nutrients and beginning the slow process of soil formation. Fungi form networks that help to break down organic matter and recycle nutrients. Gradually, these invisible communities create the biological foundation that will support larger organisms. The first plants to reach the island face enormous challenges. They must not only survive the journey across the ocean, but also establish themselves in an environment with little soil, limited fresh water, and constant exposure to salt spray and intense sunlight. The plants that succeed in this harsh environment are typically those with adaptations that allow them to tolerate extreme conditions and to reproduce and spread quickly when opportunities arise. Many of the first plant colonists arrive as seeds carried by ocean currents. These seeds, protected by tough outer coats that allow them to survive weeks or months in salt water, wash up on the island's beaches where some may find suitable conditions for germination. Coconut palms, with their large, buoyant seeds, are among the most successful ocean-dispersed colonists, able to establish themselves in the sandy soils near beaches and to tolerate the salt spray of the coastal environment. Other plants reach the island through wind dispersal. Their tiny seeds or spores carried aloft by atmospheric currents and deposited when weather patterns bring them down to earth. Ferns are particularly successful wind-dispersed colonists. Their microscopic spores able to travel vast distances and their simple requirements, making them well-suited to establish in the cracks and crevices of volcanic rock where moisture collects. The arrival of the first animals often depends on the establishment of plant communities that can provide food and shelter. Small insects and spiders may arrive on wind currents, carried as involuntary passengers in the same atmospheric systems that transport plant seeds and spores. Larger animals typically arrive by flying. Birds that may initially visit the island only temporarily, but eventually establish resident populations as suitable habitat develops. The process of biological colonization is not rapid or dramatic, but rather unfolds slowly over thousands of years as species arrive, establish themselves, interact with each other, and gradually build increasingly complex ecological communities. Each successful colonist changes the environment in ways that may make it more suitable for some future colonists and less suitable for others, creating a constantly evolving biological landscape. As plant communities become established, they begin to modify the physical environment of the island in profound ways. Plant roots help to break down volcanic rock and speed the formation of soil. Decaying plant material adds organic matter to the developing soils, increasing their fertility and water-holding capacity. The shade provided by growing vegetation creates cooler, moister microclimates that may be suitable for species that could not survive in the harsh conditions of bare volcanic rock. And so we come to the gentle conclusion of our journey through the birth of volcanic islands. Though like the geological processes we've followed, this story never truly ends. As you rest there now, breathing slowly and peacefully, you carry with you an understanding of one of our planet's most patient and beautiful creative processes, the transformation of deep earth fire into living landscapes that can support the incredible diversity of life. The volcanic island that we've followed from its first stirrings in the deep mantle to its colonization by life represents just one cycle in the endless dance of creation and transformation that characterizes our dynamic planet. The same processes that built this island are at work right now beneath other parts of the ocean, slowly preparing the birth of future islands that may not emerge for hundreds of thousands of years. As you prepare to drift into sleep, you might imagine yourself floating gently above the completed island, seeing it as it appears after millions of years of patient development. The dark volcanic slopes are now covered with green forests, their valleys carved by streams that flow toward the sea through landscapes of incredible beauty. The shores that once knew only the crash of waves against barren rock now support coral reefs and sandy beaches where life flourishes in countless forms. Yet even as you admire this mature island, the endless cycle continues. Deep beneath its foundations, the same volcanic processes that created it continue to operate, though perhaps more quietly now. The mantle plume that gave birth to the island may be moving on, following the motion of the tectonic plate above and preparing to create new islands in the distance. The existing island begins its own slow journey toward eventual return to the sea, as erosion gradually wears away the volcanic rocks and reduces the mountains to gentle hills. But this apparent ending is also a beginning, for the material eroded from the aging island doesn't disappear. It becomes part of the sediments that accumulate on the ocean floor, contributing to the geological processes that build new land elsewhere. The nutrients carried away by erosion nourish marine ecosystems and may eventually become part of new volcanic rocks, as the cycle of plate tectonics brings ocean floor sediments back into the Earth's interior to be melted and recycled. The life that has colonized the island also participates in cycles that connect the island to the rest of the planet. Birds that nest on the island may carry seeds and nutrients to other islands hundreds of miles away. Ocean currents that flow past the island carry marine larvae that may colonize distant shores. The island becomes not just a piece of land, but a participant in the global networks that connect all of Earth's ecosystems. As you continue to drift towards sleep, you might find profound peace in knowing that you are part of these same endless cycles. The elements in your body were forged in the hearts of ancient stars, just like the elements that make up the volcanic rocks of islands. The water you drink and the air you breathe participate in the same global cycles that nourish the forests and coral reefs of volcanic islands. You are connected to every part of this beautiful, dynamic planet through the same fundamental processes that create islands from the depths of the sea. If you've enjoyed this gentle journey through the birth of volcanic islands, please consider subscribing to Whispering Atom, and let me know in the comments where you are in the world as you listen to these words. Are you perhaps on an island yourself, resting on land that was once molten rock rising from the ocean depths? Wherever you are part of the same Earth that creates such beauty through patience and persistence. But for now, simply rest. Let yourself drift into sleep like the gentle settling of volcanic ash, carried by forces larger than yourself, finding your place in the endless cycles of creation and renewal. Your dreams tonight may be filled with the deep stirrings of the mantle, the patient building of underwater mountains, and the magnificent moment when molten rock first breaks through the waves to begin building new land under the endless sky. Sleep well, knowing that you live on a planet that never stops creating, never stops transforming, never stops finding new ways to express beauty and life. Rest peacefully in the knowledge that the same creative forces that build islands from the sea are constantly at work around you, shaping landscapes, supporting life, and participating in the endless dance of geological time. Sweet dreams, and may you wake refreshed, remembering that you are part of a living, breathing, creating planet that builds islands from fire and transforms barren rock into gardens of incredible beauty. The Earth's patient artistry continues even as you sleep, creating wonders that will inspire future generations to marvel at the endless creativity of our remarkable world. Good night, and dream of the gentle fires that build islands from the sea.